Hey guys, BuildZoid here, and today we're finally going to be taking a look at a DDR5-8000 setup. As you can see right here, my DRAM frequency in CPU-Z is 4023 megahertz, which is actually not completely correct because there's like a BCLK reading error. I don't know why it's reading 4023 megahertz. It should really be reading like 4000 megahertz or maybe like 3990. You get the idea. So yeah, that's a bit glitched out, and hardware info is doing the same thing for some reason. But anyway, yeah, DDR5 8000. So let's take a look at what the setup here is. So there's the system specs. This is a Ryzen 9 7900X, which was provided by AMD, so big thank you to them for the CPU. The motherboard I'm using is a Gigabyte B650E Aorus Tachyon, which was provided by Gigabyte, so big thank you to them for the board. And the memory kit is a V-Color Manta X Prism RGB memory kit. It's 2x24 gigs, and it's this is an XMP memory kit. The XMP is DDR5 8000 with the 38, 52, 52, 128, 1.4 volt. Well, that's the timings and the voltage. You can read specs. Come on, it's not that hard. Anyway, the main thing we care about is the fact that these memory sticks use Hynix 24 gigabit MDI memory chips, and this is a single rank memory configuration. And yeah, and funnily enough, this memory kit really is meant to work with Z790 motherboards. It's not really meant to be used with AMD systems, right? It doesn't have an Expo profile at all. It only has a DDR5 8000 XMP profile. But if you've been following the channel for long enough, you can probably guess roughly how well trying to run this kit went for me with Z790 motherboards. Officially, this kit is spec'd for officially it's supposed to work on the Apex and the Z790 Dark. And funnily enough, I've recently gotten an Apex, yeah, no, it doesn't work. At least it doesn't work, if I turn on XMP, it doesn't work at all. If I spend several hours trying to fix the stability, it works kinda. As in, it still throws errors eventually, but it's not completely unusably unstable. So yeah, and after spending way too much time trying to get that to stop being an Intel system, I gave up and decided to just run this on the Gigabyte B650E Aorus Tachyon because, AMD recently put out that AGSA update, which really improved the memory training, which allows the 2-to-1 mode to actually run really high memory speeds. And on a board like the Tachyon, that actually translates into a very, very stable DDR5 8000, right? Like this runs everything. So we have Karhu RAM test here at 23,000%. That ran for 15 hours. 1100% of over 1,000% of HCI. There's one thread that's way behind, and the reason that happens is there's just some load balancing issue with HCI on the dual CCD Ryzen chips. This doesn't happen on the single CCD chips. But the thing with the single CCD Ryzens is that those literally, the way the Infinity fabric is set up on those, they do not have enough bandwidth to make use of a DDR5 8000 setup. So if you have a single CCD CPU, this is completely pointless because you simply do not have enough Infinity fabric bandwidth to benefit from this. Whereas the dual CCD chips, they can actually see some uplifts in some of the really memory bandwidth intensive workloads, like say Y Cruncher. But anyway, so yeah, mem test passed. There's 100 loops of linpack, each of them lasting 44 seconds, so that's over an hour of linpack. Then we have an hour of VST, and Y-Cruncher recently got a new version which added a sort of new, a new version of the VST algorithm called VT3, which is more optimized and heavier. The VT3 is significantly harder to run than VST is, and VT3 over here you can see that ran 6,600 seconds, so just under 2 hours almost. And yeah, and so this runs everything. It doesn't spit random errors out. And the funny thing is, this was really easy to set up, which I think is mostly down to the board, because I did very briefly try this memory kit on the B650 live mixer. That did not go well. I don't think it even posted at 7,600. So, yeah, but I didn't really spend too much time with that because that was that board just happened to be around when the memory kit showed up. So I was like, hey, I wonder if it'll work, and the answer was no, not really. But on the Tachyon, like just enabling the XMP profile, that already was pretty much like that was basically already fully stable. Like the only thing it wouldn't run was VT3. Because VT3 is like very particular about some of the voltages, but everything else would just run on the XMP profile. Even like I literally went XMP and then just like tighten like tighten some of the sub timings because I didn't really want to wait for the memory stress test to take forever, right? Because like having the default DDR5 refresh interval makes memory stress testing take for absolutely forever. So I optimized some of the timings just so the stress test would run faster, and everything passed on like auto settings except VT3. VT3 was very upset about the like auto. I think it was mainly the auto VDDP, but there was like a few different voltage adjustments that I made to try get VT3 stable. Because VT3, the symptom that it like this doesn't spit out errors for some reason, it just resets the entire system when it crashes, which is like in the past, my experience with Ryzen 7000 has been that that's an indication of like core instability or Infinity Fabric instability, not really like a memory controller thing. But well, we'll get to that once we go into the BIOS. So yeah, but now it passes. Also, initially I was testing like an hour of VT3, but the first VT3 crash that I got was at like 3,000 seconds, which is why I decided to run it to over 6,000 seconds because I didn't want to have a VT3 pass where it was like, oh, I just barely, like got lucky and it didn't error out because I got lucky. So I wanted it to be properly stable. So that's just a general thing that I do with most of my stress testing these days is like if a stress test like errors out at like, let's say I was using HCI, right? If HCI errored out at like 400%, I would run it to 800% the second time around just to make sure that like it wasn't like, oh, I just stopped the test before the error would show up again, right? Kind of deal. So, yeah. Anyway, yeah, so this is like surprisingly easy to set up. In fact, it was so easy to set up that at this point I'm like actually inspired to try push it further instead of the Intel experience where I've never gotten 8000 to like work at all. But yeah. Um, so at this point, I think we're gonna go take a look at the BIOS settings because there's really. Oh, I guess here's some basic IDA. The CPU is just on stock settings. It doesn't like this doesn't really mean anything in terms of performance, though it's worth noting that the latency is not too bad considering we're in 2-to-1 mode. But like you could already have sort of figured that out because I did a bunch of like clock normalized performance testing of 1-to-1 mode versus 2-to-1, and at like 7600, 2-to-1 mode is actually not losing completely. Like it doesn't win every benchmark, but it's also not super far behind. And that's at 7600. At 8000, like it is actually viable from a performance perspective. It's just not really useful on single CCD CPUs because again, they're very limited in terms of Infinity Fabric bandwidth. And on dual CCD CPUs, like it's a bit faster. It's not, but yeah, anyway, if you were wondering about the latency, it's actually not too bad. But at this point, I guess I gotta commit to the take of this video, and let's just restart here. And I'm actually gonna shrink this down a bit. This shouldn't take too long to reboot. The memory context restore on the new AGSA, in my experience, has been very good. And I might have it disabled because it's sitting on the 15 code right now. Still shouldn't take too long to post. Like Gigabyte seems to be... So the thing with the new AGSA is that you can actually adjust the memory training duration. And Gigabyte has it set quite a bit lower than, say, ASRock has it on default. Okay, and we're in. You can also set the training duration to be like several minutes if you want. I've not really experimented with that if it like makes a significant difference to stability. Anyway, here we are in the BIOS. For some reason, it's all low res. Oh, I bet it's because I have compatibility mode on, don't I? Wait, no. Oh yeah, I do. Yeah, that's because I was messing with like old GPUs, so just ignore that. Anyway, so let's go through the settings here. So the SoC voltage, this isn't minimized. It's at 1.28 because like I mentioned earlier, VT3 was causing like the whole system to reset. Like it would just drop the whole system. No warning, no error, no blue screen, nothing. And the system would just reset itself. And like I mentioned, that's usually an indication of like the Infinity Fabric or the cores crashing. And the Infinity Fabric, in my experience, does not necessarily, it might vary by CPU, but every single chip I have hits the highest Infinity Fabric clocks at like 1.2 volts SoC. Any higher, and the Infinity Fabric starts getting worse and worse in terms of stability. So, you know, when I was setting this DDR5-8000 up, I started with the SoC voltage all the way at 1.3 volts because the memory controller clocks higher with high SoC voltage. So if you want to run like high memory clocks, you want high SoC voltage, whereas if you want high Infinity Fabric clocks, you actually want low SoC voltage, which is kind of a annoying sort of interaction between those three things, where it's like your SoC voltage has different, like optimal SoC voltage is different depending on if you want to max out FCLK or UCLK or MCLK. Like UCLK and MCLK are actually coupled, right? Like that's what this is over here. Is you have your memory controller clock locked to the memory clock, or you have the memory controller clock at the half the memory clock. We're obviously running half the memory clock because the memory controller doesn't do 4 gigahertz. It does, it can go up to like 3 gigahertz, which is why like one-to-one mode is viable for like DDR5-6000 to like 6600. But yeah, it doesn't do 4 gigahertz, so we can't use one-to-one mode for DDR5-8000. Anyway, so SoC voltage is at 1.28 because I started with 1.3 assuming that the really high memory clock would need really high SoC voltage. That turns out that, well, it may be true. I didn't test if like 1.25 SoC would be a problem, but I did start backing it off when VT3 was crashing. Similar thing going on with the VDD-IO and VDD-Q voltages. So yeah, VDD's at 1.43 because I tightened up some of the timings, and generally speaking with DDR5, your timings are primarily affected by the VDD voltage because that actually powers like the DRAM core. So the part that actually cares about all of your memory timings, or at least mostly cares about all of your memory timings, whereas VDD-Q and VDD-IO are signaling voltages. So this is what, this powers the I/O circuitry of the memory chips, this powers the I/O circuitry of the CPU. So you can sort of think of the VDD-IO mem voltage and VDD-Q as the voltage, and the DDR VDD-Q voltage as the voltage that the CPU and the memory use to talk to each other. Because of that, generally I start, like when I'm starting out with tuning, I keep them at the same value, but how you actually want to set them up depends on the motherboards. Like some motherboards will require like very high VDD-IO mem, and then they might like low VDD-Q. This is probably due to what kind of termination settings those boards have, or just the topology itself might be affecting that. But yeah, as like a starting point, I generally keep these two equal to each other because they're used for the actual signaling. But in many scenarios, you might find that actually you need like higher VDD-IO mem than VDD-Q, or lower VDD-IO mem than VDD-Q. It depends. It really depends. And with this system, what's kind of nice is that this might just be down to the Tachyon being just amazing. A lot of things work. Like the XMP profile for this memory kit, right? That loads up 1.4 volts across the board. Like that's just 1.4 VDD-IO, VDD-Q, VDD. That worked for everything that wasn't VT3, right? And I haven't gone back and checked if 1.4 volts across the board would work again, like in VT3, because ultimately the last thing that I adjusted that fixed the VT3 stability was the VDD-P voltage. Which I had to drop all the way down to 1.05, which is very low. For comparison, on the like live mixer, anything other than like 1.15 volts at like DDR5 7600 just wouldn't work. Then again, that was with Hynix A die instead of 24 gigabit M die, so maybe the memory chip would affect it. But I think it's more likely that it's affected by the actual motherboard. Now, these two voltages over here are two voltages that I've been messing around with on and off because on at least Ryzen 5000, you had like the 1.8 volt rail or one of the 1.8 volt rails would significantly affect the FCLK stability. Um, so far, I have no evidence to prove that it does the same on Ryzen 7000, but I take the opportunity to check every so often. And yeah, I bumped these when trying to get VT3 to stop crashing. I don't think they actually help. Like, I don't think it actually helped, but they're still here because that was one of the last adjustments I made, right? But I'm pretty sure that VT3 was just complaining about the VDDP voltage being too high because that was like the very last adjustment I made was setting VDDP to 1.05 and that fixed, well, after that VT3 didn't crash anymore. So, yeah, other than that, I also lowered the VDDGs to 950 because the board was defaulting them to 1000 millivolts. And in my experience, especially the IO die voltage, if some on like, and this might have changed with the AGSA updates, but definitely on earlier BIOSes, I've found that if you had the VDDG IO die voltage set like above 950, or especially if you set it to like 1000 or higher, it would cause random like crashes at idle where the system would just kind of reset itself. And I thought that VT3 was maybe triggering sort of the same thing. So when I went into the BIOS and checked the VDDG voltages and saw that they were both at 11, like at 1000, I figured, okay, maybe I should lower them. And that's how they ended up at 950. Are they actually optimal at 950? I don't know. I haven't checked, like, I haven't gone through like a full range of voltages, and it's possible that as I, like, I do want to try clock this even higher past like DDR5-8000 because like this was too easy. This didn't take a week to stabilize, And honestly, like at 8000, there's like a variety of different settings that work, so this isn't on the edge yet. So it's possible that if I start pushing it further, I might have to raise the VDDG voltages back up again. But honestly, for FCLKs below like 2100, I don't think that'll be necessary. It's only once you start, and it depends on the CPU, but it's only once you start pushing past like 2100 FCLK, in my experience, that the VDDG voltages start needing to be raised. Now, that might be different when you're at DDR5-8000, but at least to like 6200, yeah, like from like 2000 to like 2066 FCLK, you wouldn't have to raise these above 950. Anyway, so that's those. So from this, basically, like, things that make sense here is like the VDD misc voltage being at 1.1, that's stock. VDDP, that's actually necessary to get VT3 to not crash. These are just sensible VDDG voltages if you're not like trying to push the FCLK super high. So anything below 2100 FCLK should work. And if you're lucky, your CPU might do even 20, like, I think the 7800X3D in my daily system will do like up to 2160 FCLK on 950 VDDG voltages. So there's a lot of chip-to-chip variance on that in my experience. Anyway, these two, on the other hand, I would just ignore that. I don't think those actually made any difference to the stability. They were just something I was messing with, and that's still here because I'm not gonna, remove things, like rerun everything after, like, they're also not going to harm the CPU, right? Raising a 1.8 volt rail to 1.82 is not going to break anything. So, yeah, other than that, I bumped the SoC volts, the load line calibrations to high because I kind of suspected that VT3 might have been crashing the core, even at stock settings, because Y-Cruncher has a reputation for doing that sometimes, is that like certain systems, even at bone stock settings, will just crash running Y-Cruncher because it's that freaking heavy and also very transient as a load. And so because of that, I sort of tried to bump the load line calibration to high. Now, this makes the voltage regulation actively worse, but the idea behind doing this is because your load voltage goes up a bit, it should get the CPU to throttle back the boost clock a little. So this actually hurts performance very slightly, but it should prevent the crashing. Because like the other option I had was like to intentionally somehow like underclock the CPU, which could have been done with like a positive curve optimizer offset, right? Like I could have bumped the curve optimizer positive to, and between the two of them, I figured, and bumping the LLC is probably the least bad option, and probably wasn't necessary. Like ultimately, what got VT3 to stop to stop the resets in VT3 was the VDDP adjustment I made, but I've not gone back and like retested undone everything that I tried when trying to get VT3 stable. So anyway, but these are up at high, probably unnecessary. But that is something to keep in mind when running Y-Cruncher, is that it can actually sometimes crash like bone stock CPUs. Especially, I would assume, especially if your motherboard's VRM is kind of garbage in terms of voltage regulation, but I've not done like a ton of testing on that yet. Anyway, I don't think I have anything in precision boost. Yeah, no, I didn't do anything. Like, I think at one point I was testing a positive curve optimizer offset to see if like it was actually the CPU core causing the resets, but no, it wasn't. It was the VDDP voltage. Anyway, yeah, also I have the Infinity Fabric at just 2000 because apparently it actually syncs up at, because with DDR5-8000, the memory is at 4 gigahertz and the memory controller is at 2 gigahertz, so that can actually synchronize with the Infinity Fabric at 2 gigahertz, which gives you a very slight latency reduction. The funny thing is that latency improvement is like not as big as it was on the like 5000 series, at least from like from my testing, because you can very easily overcome that by just running high Infinity Fabric. Like even like 2100 should be enough to completely negate the benefits of the sort of like coupling of the Infinity Fabric. Now, I don't think it would. I think it might actually result in like IDA reporting a higher latency, but if you run actual benchmarks that are like memory performance and memory latency sensitive, you'll find that high Infinity Fabric very quickly just sort of negates the desynchronization penalty with Ryzen 7000, probably because Ryzen 7000 has like a really imbalanced memory system if you think about it. The Infinity Fabric really doesn't have that much memory bandwidth compared to the memory controller itself. So yeah, just kind of brute forcing the data through with more speed seems to be much more viable than it was on like Ryzen 5000, right? Because like on Ryzen 5000, you wouldn't go and run your Infinity Fabric at like 2100, mostly because it wouldn't be stable, but you wouldn't run like 2100 Infinity Fabric with DDR4 3600, that would probably actually be faster. Because that was the thing. Like, if you were on Ryzen 5000, if you were running memory like DDR4 3200 memory, you're better off running the Infinity Fabric at like 1866 than running it at 1600, because like the extra bandwidth and just speed of the Infinity Fabric negated the penalty of having to buffer the data between the Infinity Fabric and the memory controller. So Ryzen 7000 kind of like the buffers seem to be more efficient than they used to be. Because on Ryzen 5000 and 3000, you needed like a big gap between the memory controller clock and the FCLK for that to make sense. Like if you were at like 1600 memory controller, 1800 Infinity Fabric would be faster, or 1866, something like that. But if you were at like, I think 1533 was a ratio. No, 1533 is lower. 1766, I think. You would actually want to be synchronized for like 1766 and 1733. Yeah, something like that. Anyway, let's take a look at the memory settings. Didn't disable power down mode. This would actually help reduce the memory latency a little bit, just because the memory controller wouldn't have to wake up the memory sticks. The funny thing about power down mode is I'm relatively certain it doesn't affect, like it shouldn't affect performance under high memory load, because the memory controller won't put the memory sticks to sleep. Because power down mode is like a sleep state for the memory sticks. And you won't, like, if the memory sticks are, like, if you're reading and writing data, you won't be putting them to sleep, right? So I'm pretty sure this only affects, like, IDA style, like, IDA latency, because the IDA latency test is very light. Like I've seen, especially with Ryzen 7000, one of the issues with the IDA latency test is the CPU can sometimes not turbo for it, and then your latency goes through the roof because your CPU will be at like 4 gigahertz instead of 5. So yeah, that's fun. But anyway, so I have that enabled, but disabling it can improve latency. It can also cause like weird stability issues. So, considering how much difficulty I've had with getting DDR5-8000 to work on Intel systems, didn't really want to risk it. Anyway, let's take a look at the actual timings. So 36, 48, 46. MDI does lower TRP than TRCD. Not as much as ADI does. Like on ADI, you could sometimes run your TRP like 5 or 6 cycles below, or actually maybe even lower than that, below your TRCD. MDI doesn't go that far below. Also, I tested TRCD 46. That does not work at the current like voltage settings I'm at. I think maybe if I could run VDD at like 1.6, it might do 46, but I am not sure if the PMIC on these memory sticks is properly compatible with this motherboard, because Gigabyte has this really annoying bug where high voltage mode for DDR5 sticks on their boards doesn't work quite right. So on some memory sticks, if you try to go over 1.435 volts, the system just fails to train, or more like it just gets stuck trying to post. So, yeah. Anyway, so TRP is slightly below TRCD. TRCD is basically minimized. I didn't test 47, but 47 and 48 are kind of the same thing. On that note, running TRP at 48 would also make basically no difference to performance, because 46 and 48 are kind of the same thing. Like the difference between 48 and 46 is so small that it's just not really going to make a big difference to performance. But because, this is Hynix MDI, you can be pretty confident that if your TRCD works at 48, then TRP probably works at 46. Anyway, TRAS is at 40. This, I didn't experiment if it would go lower, mainly because I didn't experiment with TRC. So the way I always set TRC is that TRC is equal to TRP plus TRAS, because that way you can be certain that TRC actually does something. And I didn't test if like lower TRC values would work. If they do, then I would have been lowering TRAS to match that. So if say let's say 80 works, then I would be running a TRAS of 34 to match with that, right? So 34 plus 46 is, right, is that 80? Yeah, that's 80. But anyway, I just also lowering your TRC by 6 cycles. This actually would make probably more of a performance difference than tweaking TRP by 2 ticks, but 6 cycles of TRAS are, if you're running benchmarks, sure, but if I'm going to run all of these stress tests, I don't really want to be dealing with fine-tuning TRC by 1 tick at a time. So anyway, TWR is minimized. You cannot set it below 48 on Gigabyte motherboards. Some motherboards will let you go below 48, but I am not sure if that's because, I'm not sure if that's actually supported by the memory controller. Because some motherboards just don't enforce timing limits, right? So the CPU might, some motherboards will let you set the TWR to 40. I don't know if the memory controller doesn't just auto-correct that to 48 anyway. And I'm not sure there's any way... And the annoying thing with a lot of these small timing adjustments where 48 versus 40, that's such a small adjustment on a timing that only affects the delay from a write operation to a pre-charge, which is an operation that the memory controller can relatively easily hide behind other operations. The whole idea behind memory is that the way DRAM is designed to work is that you run a lot of different commands in parallel with each other. That's why there's so many memory banks, so that each memory bank can be working on something else from the other, so that you can basically hide the fact that each individual memory bank is actually really freaking slow. But anyway, so because of that, it's kind of hard to test if, being able to set the TWR below 48 actually does anything. I kind of suspect it doesn't, but anyway, it doesn't matter. 48 is way lower than the XMP profile. Actually, you can see the XMP timings right in this middle column, and yeah, they suck, which is normal. You wouldn't the thing with XMP profiles is they do actually need to work, right? So performance becomes a secondary priority to actually not blue screening constantly, unless you have an Intel system, because DDR5-8000 doesn't work on those. Anyway, or at least doesn't work without bending over backwards. Anyway, TR-EFI is maxed out at 65,000, which, yeah, is like, that's actually sort of the biggest performance uplift you generally see on DDR5, is because the stock TR-EFI is really, really short, which means the memory spends a lot of time refreshing. Actually, if we do the calculation for this, and let's see, do I have a calculator? There, so, ta-da. So if we do the calculation for this, the XMP TR-EFI and TRFC here are 1,636 for the refresh cycle, and the refresh interval is 15,600 clock cycles, which means 10% of our available clock cycles are spent on refresh. Literally 10% of your available memory clock cycles are spent just refreshing. So on DDR5, adjusting the refresh interval is like one of the biggest performance uplifts you can get. And actually DDR4, it's similar. I don't think it's quite 10%. I think it's slightly smaller. I think DDR5 is like heavier on, like, has more refreshing, probably because of the speed and the density. But anyway, yeah, for comparison, what I'm running right now with my 800 TRFC, which isn't minimized, I haven't checked if lower than 800 would work, but like 800 over 65,000, what is it, 65535? Yeah, that's a 1.2% refresh. So literally we are refreshing like 10 times less often, which means we have about 9% more clock cycles available to actually, you know, transfer data, like do read and write operations with. So, yeah. Anyway, and admittedly, like, I'm not sure that, well, I haven't checked how low the TRFC will go with these memory sticks yet, but, at this point, like, it's very diminishing returns, because let's say it did, like, let's say it bottomed out at, like, 700. That would only be like a 0.2%, like, you know, we'd go from 1.2% refresh to 1% refresh, which is not really that big a difference at that point. So I'm not too fussed about, like, minimizing the TRFC at this point. In fact, with the refresh interval being as high as it is, I don't think even the, like, 1600 clock cycle refresh cycle would actually be that bad at 65,000 interval. Yeah, it would be about 2.5%. So, you know, yeah, like, it's it's quite a bit worse, but it's not a complete disaster. Oh, I have another calculator open. Anyway, yeah, then TRFC2 and TRFC same bank, I have those on auto because as far as I know, the AMD memory controller still doesn't use these two timings. There's like, DDR5 has two refresh modes, one where you refresh very infrequently, but for a long time, which uses TRFC1. And then there's a fast refresh, like a very frequent but short refresh mode, which uses TRFC2 and TRFC same bank. Intel uses the more like faster refresh setup with shorter, like the more frequent refresh with shorter refresh cycles. AMD uses the like less frequent refresh with longer refresh cycles, at least as far as I know. So TRFC2 and the same bank aren't used on AMD CPUs. TRP's at 12. I didn't check if it goes below that. It probably doesn't, and even if it does, it's not going to make a huge difference. Also, I think it bottoms out at, oh, it can go really low. The thing is, RTP just controls the delay between a read command and a pre-charge. Not like, basically, like, RTP and TWR are kind of the same situation where it's like, it's a pre-charge command. The memory controller generally kind of hide those pretty well. Unlike, say, an actual read operation, right? Like a read and an reads, activates, those are like latency critical operations because you're trying to get at some new data. Whereas read to pre-charge, write to pre-charge, generally they're like, oh, I've already got the data I want and we're moving on to something else. So those are, from a performance perspective, less important. The same applies for like TRP to some extent. Now, obviously, your pre-charge commands can be in the way of new activate commands that are trying to get through. So, you know, but like you have, what is it? 8 bank groups with 4 banks each on DDR5, so there's like 32 banks in total. It's kind of unlikely that whatever you're trying to get at is in a bank that's currently pre-charging, right? So, or that's like is currently in a bank that you need to pre-charge right now. That's sort of the thought process there. Anyway, TRRDL and TRRDS are at 12 and 8. I don't know if they would go any lower. I have heard that TRRDL for 24 gigabit MDI won't go below 12, but I've not verified that myself. And TRRDS I've not tested either if it will go any lower. It might not. The TRRDL isn't really a big deal. Like, neither of these is really a big deal because TRRDL is same bank group, like consecutive activate commands to the same bank group. The memory controller will generally avoid doing that if it has the option not to do that. And with DDR5, you have a lot of bank groups. It's statistically unlikely that you're going to have to frequently send activate commands to the same bank group. So that timing isn't like between TRRDL and TRRDS. TRRDS is significantly more important for actual performance because the memory controller, like if things are going ideally, you wouldn't have to use that timing at all. Like, so anyway, now TRRDS is at 8, which is a lot higher than what I usually go for with AMD, which I usually aim for like a 4. But what you need to consider, like, going from 8 to 4 is less of a performance uplift than actually, like, say, from 12 to 8. And the reason for that is that the burst length on DDR5 is 8 cycles. So actually having the ability to send an activate command every 4 cycles instead of every 8 cycles doesn't really change how dense your, like, read and write operations are going to be afterwards. It can offer some benefits to the memory controller in terms of like flexibly, like doing all the activates in less time. But when it actually comes to reading and writing data, like that's ultimately limited by the 8 cycle burst length. So the TRRDS being at 8 instead of say 4 isn't really the end of the world. Now on DDR4, where your burst length is 4 cycles instead of 8 cycles, having a TRRDS of 8 would be really, really bad. Like really, 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 really bad. Because you'd have a 4 cycle gap between like your read and write operations for like eventually the memory, like eventually everything would queue up so that you have like full saturation, but your initial like read, like your first couple reads and writes would have gaps between them, which is not ideal, right? Like with memory, like from a performance perspective, your goal is to have every single clock cycle actually moving data is the goal, right? So TRRDS 8 is already basically capable of doing that. Or not even basically, it's literally capable of doing that. But 4, like having a 4 could, in some scenarios, give the memory controller more flexibility. Anyway, TFall32, because, I mean, technically I could have set it to 20. It wouldn't make any difference, because what this governs is the minimum number of clock cycles for activate commands. And so, considering that our activate to activate timing is 8, the short one is 8, well, 4 activate commands are going to take at least 32 clock cycles. So TFall32 and TFall20, and with these TRRDs, is going to perform the same. So honestly, I could have put in 20. There's really no reason that it had to be at 32. WTRL is at 24. I don't know if it would go lower. I didn't test. I think I did do like a theoretical calculation of like it should probably be somewhere around 20. And I erred on the side of caution with 24 because I didn't really feel like rerunning the stress tests. I am traumatized by DDR5-8000 on Intel systems. Anyway, WTRS is at 6. It might go lower. I didn't check. Same reason as WTRL. At this point, though, it's not like these are both already significantly lower than XMP. So from that perspective, like this is a win. Anyway, RDRDSCL is at 9. Might go lower. I didn't check. It probably won't go below 7, though. So this is not going to see some massive performance uplift, even if I try to push it down at this point. WWR, on the other hand, this could probably go significantly lower. Oh, also the read-to-read SC, that's at 1. It doesn't go below that. Which is kind of funny that the AMD memory controller has like a... Well, whatever. It doesn't matter. WRWRSC is also at 1. It doesn't go any lower than that. But WRWRSCL, this could probably go 2 ticks lower than TRRD-SCL, but again, well, write operations generally aren't as important for performance as read operations, and I didn't feel like dealing with stress test crashing. So, yeah, and then we have write to write, TWRRD and read to write, so write to read and read to write, and these are at 7 and 22. They might go lower. I didn't check. Though I think these are the auto values for these two. These might be from the board itself, and I just like copied them in so that they wouldn't randomly change as I was making other adjustments. Other than that, everything else is on auto because the board just handles that just fine, at least for DDR5-8000. Yeah, I don't think there's anything else that I haven't mentioned. Yeah, I don't think there's any other adjustments that I need to mention. This was really, really easy to set up. I think most of that is down to the board. Because, again, I did try these sticks on a B650 Live mixer, and there I think I maybe got 7600 to post if... I'm not sure. I don't think I did. But yeah, on the Tachyon, like, the XMP profile basically works. Like, it runs VST, it runs memtest, it runs RAM test, it runs linpack, you know. And then the only thing I really needed to fix was, like, VT3 stability. And when I was fixing the VT3 stability, I also took the opportunity to tighten some of the timings further. Because my initial test run was, like, I just raised the TREFI. Because, yeah, for the initial test run, I think the only things I adjusted was, like, I kept the primary timings on auto. I maxed out refresh interval. I dropped TRFC to 800. I think I dropped the TRRDs to 12 and 8. And actually, no, I don't think I even changed those, because on auto, they go 15-8. I think they go 15-8. On this board. But anyway, and then I dropped, like, actually, I think read to read SCL was already at 9, and I just dropped write to write SCL to 9 as well. Because for some reason, the DDR5, like, JDEC spec has the write operations really slow. Like, back-to-back writes are just crazy slow for some reason. Like, it defaults to, like, 30 or something, which is weird, because, well, actually, I think there are some ICs that can't do quick writes back-to-back, but Hynix memory chips very consistently can do write-to-write operations really, really fast. Like, faster than they can do read-read, like back-to-back reads. So, yeah, I'm not entirely sure why the default write-to-write is always, like it's sky-high compared to the default read-to-read timing. Anyway, so, yeah, and, like, even auto voltages basically worked. Like, the only thing the original setup was, like, 1.3 volts SOC, and then all of the other voltages was just what the XMP profile used. Which is, like I can't believe that worked. It ran everything except VT3. If I did, like, on Intel systems, it's just like, nope, that's not gonna happen. Yeah, so... big thank you to V-Color for this kit. And I do plan to push it higher. Also, like, I finally have a 24 gig kit to just test in general. I feel like it's a bit unfortunate that it came with an XMP 8000 spec, because on basically the vast majority of at least Intel systems that I have, I can't run it anywhere near that. Like, you know, like, normally these videos are like, oh, DDR, like, memory overclocking videos. This kit, on, like, most Z7, like, this is an underclocking memory kit for like, Intel motherboards. And actually most AM5 boards as well. Like, I do want to test this kit on some 4-dimmers, because it's cool that it works really, you know, at, like, DDR5-8000 on a Tachyon, but this board is very low production. Like, I don't think, like, as far as I'm aware, there might not even be 2,000 of these boards in total. And it did technically get a very limited retail release. So it's not just an engineering sample board that nobody could buy. But as far as I know, basically, if you didn't already manage to buy one, that's it. Like, they sold out. So, yeah, the fact that I have this working on a very low production motherboard is kind of... Like, I'm happy that it finally, like, I finally got DDR5-8000 to work, and the performance is cool, but this isn't practical. really, right? Because how many people actually have this board? Um, so yeah, but hopefully now that, AMD has like the 2-to-1 mode, like now that AMD's 2-to-1 mode is actually not completely useless, because at launch 2-to-1 mode didn't clock any higher than 1-to-1 mode. Maybe Gigabyte will produce more tachyons. I'm kind of hoping for that. Because yeah, cool board, cool memory kit. I will put well, man, I'll try a little bit to get this to work on some Intel boards, but I don't have high hopes. I've already sunk like endless hours into trying to get DDR5-8000 to work on Intel systems. It never does. And honestly, like on AMD, like I didn't have to do anything other than fix the VDDP voltage. Like, that's it. That's all I had to do. I had to lower the VDDP voltage a little bit, and bam, everything runs. Meanwhile, on Intel systems, I need to bend over backwards just to get VST to not, like, immediately crash. And so, honestly, yeah, I don't know. I don't think, like, I'm not sure that I'll show, like, a stable overclock with this kit on an Intel system, because it just... I'm probably doing something wrong, but it seems ridiculous to me that AMD can put out like one AGSA update and DDR5-8000 magically works on 1 DIMM per channel motherboards now. Meanwhile, also it boots DDR5-8000 on like some 4-dimmers. Not with this kit, but with like other kits. Yeah, so that's kind of that. I do really want to try push this kit even further on this board. Not on Intel motherboards. Funnily enough, I did boot 8600 on the Z790 Dark, which is, I think, the highest memory speed I've gotten to boot on the Dark. Admittedly, I didn't really put much effort into that, because, yeah, like, and that was with 2 sticks, not just one. Because ultimately, like, the fact that it boots, like, 8600 is neat and all, but, I mean, well... well, on one hand, I do enjoy memory frequency validations, but on the other hand, I don't enjoy making, like, not good video content. So that's kind of the conflict that this channel has at this point, where it's like, oh, I got sent a memory kit that, like, it's not a daily memory kit as far as I'm concerned, because the stability is just so hard to achieve, at least in my experience so far. Then again, I have probably some of the worst 13th gen Intel CPUs ever made in terms of the memory controller, so yeah, that's it for this video. I guess I heard it here first. AMD's support for ridiculous memory speeds is far better than Intel's, because the memory like, it just works with so many different settings. Like, and also it's consistent. Like, boards that don't work at 8000, they just don't work. And boards that do work at 8000, they do work. So yeah, anyway, that's it for the video. So thank you to AMD, Gigabyte, and V-Color for the hardware that I used here. I will definitely be making another video, like, seeing if I can get the kit to run even higher speeds, but yeah, that's it. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store, where you can pick up shirts, hoodies, posters, the usual YouTuber merch. There's a link to that in the description. And I've also got a Bandcamp. There's a link to that in the description as well. And yeah, that's it for the video. So thank you for watching, and goodbye.